Hello.
Testing. Okay, we'll continue with compactness. Okay, compactness. Um, okay, yeah, today we'll focus on uniform continuity. Okay, so before we do uniform continuity, we will do a lemma called the Lebesgue number lemma. Before that, there are two pieces of definition maybe you are familiar with. First is the definition you saw in the assignment. Okay, so now we will focus on metric space first. If X is a metric space and A is a non-empty subset of X, then for every point in X, we define the distance, okay, from the point to a set. A set. Okay. So what's this set here? Sorry, what's this distance here? What's the distance from a point to a set? You remember on your assignment? Huh? Infimum. Okay, infimum of all the distance from X to some point in A. Okay. Then we will define something called the diameter. Okay, diameter of a bounded subset. Okay. So what's the diameter then? What do you know about diameter? You know diameter of what? Circle, huh? Okay. Well, diameter of circle is what? What's the diameter of the circle? 2 times radius, huh? So what does this diameter capture? 2 times radius. What does it mean here? What does this 2 radius distance cover in your circle? What do you think? Can your distance between any 2 points in your circle exceed 2 r? More than 2 r? Cannot, right? Okay. So motivated by this, we'll define the diameter of a bounded set A of a metric space to be the sup, okay, sup of the any 2 points in your set. Okay, the largest, the least upper bound of the set here. Okay, you look at all the possible distance and then look at the least upper. Okay, how you achieve 2r in your circle? How you achieve 2r? How do you achieve 2r in your circle? What 2 point give you 2r? Huh? Sorry? 2 point on the boundary of the circle. This. Huh? So they are called the antipodal. Okay, antipodal point. Okay. A line through origin that intersect with your circle. Okay, these 2 points has a distance to r. Okay. If others, maybe you get something less than 2. Okay. Okay, so there's a very powerful lemma here. Let's see how far we can prove it. So this lemma is called the Lebesgue number Lemma. So Lebesgue is a mathematician. Okay, how's Lebesgue. G. So what does this lemma doing here? So since this name got number, right? So number is important here. So what kind of number is important here? So let's see. So let A be an open covering for your metric space. Okay. Does it make sense or not? Open covering with a metric space. You have the metric space, then there's a topology that's induced by the metric. Okay, what's the topology induced by the metric? Yeah. The topology generated by your open bow. Okay, because once you have distance, you can define what's the open bow. So if X is compact, okay, so compact the sense of the open covering here, then there exists a delta here. Okay, there exists a delta such that what can this delta do? For every subset of X with diameter we give diameter less than delta, then there exists a open set in this open covering here such that B is contained in A. Then this delta here is called the Lebesgue number for the covering. Lebesgue number for the covering A. Okay. Okay, imagine what's this doing here. Okay, yeah. So let's read again. So we have a metric space, okay, and then we have open cover. So you cover with open set here, bunch of cover open set. But X is compact here means what? For this open cover, right, you should have a finite subcover. Okay, so you need finitely many open set to cover your X. Then okay, so let's draw it. So you got an X here, right? Okay, and then you got some finite open cover. Finite open cover, let's say like this. Okay, finite open cover here. Cover your X. Um, then there exists a delta. Okay, there exists a delta such that for every subset B having diameter less than delta, so if you have a set B, okay, with your diameter less than delta here. Okay, I just draw you the circle case. If it's not the circle, you need to use the soup to help you. Then there exists a open, there exists a open set, okay, in your open covering that contain this diameter less than delta subset. Make sense or not? Okay, this one is very strong. Why is it strong here? This delta will work for any B that has diameter less than this number. You get what I say or not? For example, if this delta works right, then I can look for another soup here. Oh, sorry, another set with diameter less than delta. Then this theorem tells me that there is a open set that contain this set here. Okay, from A. Make sense or not? Okay, so that's why this number bears a name called the bad number. Okay, it's quite kind of strong. Okay, no matter how you construct, no matter how you construct a B, a set B with diameter less than delta, right? There is another open set. Okay, so how on earth to prove this? How on earth we can prove this? But when is a set open? When is a set open? Do you remember? Open in the matrix space. When is a set open? When it contains an open ball. Okay. So the trick we're gonna use here is obviously we have to find this delta lah. Okay. Obviously we need to find the delta here. But what you're gonna see in the proof is if I pick any point inside this B here, and I can make sure that the ball of radius delta, with a center inside the B here will live inside one of the A. Okay, will live inside one of the A. If we can do this, we are good already. Okay, we just see that there's a ball inside one of them. Okay. Is it obvious that this ball of delta contains this set here? Is it obvious? Obvious, right? Okay. Because the furthest distance between the 2 points inside the set is delta. Okay, and then you pick any point as not here. Then you draw a delta. Should cover everything. Okay, right. Let's see what's the technique here. Maybe I break into some step for you to follow. Okay. Any question? Any question on this statement here? Any question? Yeah? Any question? Hmm. No. So for every A, for every A there exists a delta such that for all B there exists a small the capital A. Mhm. You mean script A or capital A? Okay, capital A, yeah. Capital A is okay. Capital A here is dependent on could be dependent on B. Does it make sense? Yeah. This A here could be dependent on B. Okay. So for every come first means you already pick one B already. And then this B got an A. Okay. If the order swap is different, for one there exists an A for all B. So for example, this case, right, there exists a delta for all B. So there's really one delta that works for all. Okay. Yeah. Okay, good. All right, so let's see what is the setup we have here. So let A be an open covering of X. Okay. Well, if X itself, okay, is an element of A, so meaning you use X to cover your whole set. Okay. What do you think? What Lebesgue number you can pick here? If your A contain X, okay, what number delta you pick so that all these can be satisfied? Huh? Number. I need a number X here, a delta here. What's the number that you need to pick such that this line will satisfy? If if your A, your script A contain X already, diameter of X, other than diameter of X, can it be something smaller than diameter of X or not? Can it be something smaller than diameter of X? Huh? If you are something smaller than diameter of X, are you still living in X? Yes, right. So actually doesn't matter what delta you pick here. Okay, if x is in your okay, so if you like this delta actually depend on script A here. Okay, this delta actually depend on script A. If x is already in is one of the open set you use to cover A, then any positive number, okay, is the bad match, the bad number. Okay, the bad number for A. Okay, so you see that this line here suggests that this the bad number here actually depend on your covering. Okay, so you give me one covering, if my space is compact, I can go and look for this number, the bad number here. Okay, so now this case is quite boring. So let's assume that X is not an element. It's not. So let's assume that X is not an element of script. Yeah, let's see if we still can satisfy that special condition for all diameter less than delta. Okay, so in this case here, how should we find this delta? How should we find the delta here? At this point, I will still haven't used compactness. So, okay, if we're gonna use compactness now, what does compactness does to the script A? Zhao Shen, what does compactness does to script A? Script A is the open covering of a compact set, right? So, so we can consider finite sub collection, okay, from your script A, let's say A1, A2 up to AN, okay, such that they cover X. So the union of this set is X. Okay, now is the trick here. So let's do this trick here. So we will consider this function. So what's this function here? So set Ci equals to X minus AI. So AI is open, right? So complement of AI is closed. So we build a bunch of closed set now. Then we're going to define the set here. F from X to R. So what's this function here? We send this point to the average. Okay, average of the distance of this point from all these complement of AI. Okay, average. Okay, maybe it's not apparent why we do this yet. But can you imagine what we are doing here? So let's bring this picture down. Okay, so let's say we want to compute what is Fs naught here. Wow, there are too many, right? Let's reduce this. Okay. Here we got this. Let me draw something like this. Okay, to make our life easier, let's just use 3. Okay. A1, A2, and then A3. So let's say n is 3. Okay, so what does it mean by d of x to the complement of AI here? Okay, so if you want to calculate the distance, for example, d x naught to C1. Okay, ds naught to C1 means what? The distance to the complement of C1 here. Okay, but already stay inside the complement, right? To be 0. Okay, and then how about d of S naught to the complement of A2? But the complement of A2 already contain S naught to be 0. So how about D of this point to the complement of A3? Okay, so but this point is staying inside A3, right? So you stay inside this classroom, so you have some distance from outside. Yeah. And then maybe then we will add out this number and take the average. Again, note that this is what you've done in assignment, right? Note that f is continuous. Okay. It's just can I say composite? Okay. Yeah, composite of a continuous function. Right? You add composition include addition or not? No. Our composition is just composing. This is the addition of sum of two continuous functions, right? I mean, sum of finitely many continuous function and then a scalar multiple of it. So that should be continuous. Okay. And we claim that actually this function is non-zero. Not only non-zero, strictly greater than zero. Okay. Strictly greater than zero should be obvious, right? Because distance is a positive non-negative function. Moreover, it cannot be zero. Okay, so it's strictly greater than zero. Is this clear why? Is this clear why? Why this one should be greater than zero? I think just now the way I described to you, you should see it, right? You must at least stay in one of the open cover. If you stay inside one of the open cover means what? You must have some distance from outside, from the complement. Why? Because you can find that contain this point which contain inside the open set because the set is open. You know? Okay, so for example, Joshua is at least one table away from outside. At least. This is the epsilon. Okay, at least. Does it make sense? Understand what I say? Okay, so let's write down what we discussed just now. So given an x in x, okay, then because AI will cover the whole space, right? Then we just pick an I so that this x live in. Then we can choose epsilon such that there's a ball around x that live inside AI because so let me write here because AI open. So meaning what? So this means that you are at least epsilon away from the complement. Okay, so that your fx is greater or equal to epsilon over n. Okay, because just now we average the function. Okay. Okay. Could be more. Could be more because you might have some other epsilon here. Okay, you might have some other epsilon from different C, J. Okay, could be more, but this one is one of the non-zero term. It's enough already. Okay, I want strictly brilliant. All right, so now this is a continuous function. So next step. So since f is continuous, right? And then the domain is compact. The domain is compact, meaning we can use the string value theorem. Okay, you can generalize our argument on the compact closed bounded interval, closed interval, okay, to any compact set. Okay, then it means that it has a minimum value delta. Okay, so you need to achieve this minimum. But just now we proved that fx is always greater than 0. Okay, so the minimum should be also greater than 0. Does it make sense? Okay, must achieve a minimum greater than 0. Otherwise, you can, if you don't believe, you can otherwise try with contradiction. Okay, I have a contradiction in my notes. Contradiction where delta equals 0. Okay, you can try this contradiction here. So you see, it's not an accident we want to name this as a delta. This is the bad number we want to suggest. Okay, which is the minimum, okay, of this function, the value of this function. Okay, so we want to show that. So next step, actually, this is the delta we want. Okay, actually, this is the delta we want. So we will follow the strategy that we discussed in just now. Is to find to build a ball. Okay, to build a ball around our set with diameter less than delta. Okay, so we pick a point from a set B and then build a diameter with this exactly the same delta. Okay, delta radius ball. Then show that this ball lives inside one of the egg. Okay, make sense? Well, let's see how it works. So since we have to show for all, right? So just take an arbitrary subset of x of diameter less than delta. And then we're going to choose the point from B. Okay. Then, okay, from what we discussed just now, this B should live inside ball with radius delta. That's not. Okay. Then we want to claim that this B of S naught is living inside some AM. So which AM we want to pick here? Any idea? Which AI we can pick here? Which I? What do you think? What do you think? What I we can pick here? Any guess? Any guess? What I we can pick here? Obviously, you need to think from the function point of view. How do we build our function? Average of the distance from all the complement. Okay, so what kind of inequality you can write down here? So this number delta, right, surely less than the value of fx naught, in particular for s naught, every value of f, in particular for fx naught here. But this value at the same time is less than the distance of s naught to cm for some cm, okay, where dx naught cm is the largest of the numbers d of x naught ci. This class learns statistics, right? Did you learn? No, no learn statistics? How come? I thought this is a major code. You learn statistics, right? Just now we're taking average, right? Then your average should be less than the largest number in the sum. Okay. 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 So now we're gonna claim is what we're gonna claim here is next claim. Then this ball here, b of x naught, live inside AM, where this AM is the complement of CM. Okay, this is the final claim. Dawson, can you see why it's true? Huh? Can you see why it's true? Cannot. Okay, cannot. You use contradiction. Okay, so otherwise, if it is not true, meaning what? There's some point inside this ball. Okay, but this point is not staying inside AM. Okay, let's see if we got any contradiction or not. So this means what? This means this point here is not staying in the complement of CM, which means what? This point will stay inside CM. Good. This means that the distance between Y and CM is what? 0. Good. Okay, so the magic is here. Magic lie in the triangle inequality. So if we have a delta, okay, but this delta is less than equals to d of x naught cm. Just now we established this. Okay, must be strictly less than or equal to the largest distance. But we can do triangle inequality here. Not trivial, but also not too hard. Okay, because there's subtlety here, right? Because one of them is a distance with a set, one of them is distance with point. But you should try and show yourself that this can be implied by the triangle inequality plus the increment thing. So you need to show for show for every small cm first, and then you deduce for increment. But what is this? We show that this term here goes to 0, right? Second term goes to 0. Then this is just equals to d of x naught y. Any contradiction? Any contradiction? We show that this d of x naught y is strictly greater than delta. But where we pick y from? Huh? One more. We pick from some ball. This distance should be less than delta, but we show that it's greater than delta. Okay, so this will contradict the choice of. Okay, so it must stay inside. Yeah. Okay. Any question? Which one? This one. Probably it should follow from increment thing, I guess. Yeah, try and write this part out, see this is correct or not. I think I'll try and edit it later. Even if it is equal, still work. Yes, because the ball is strictly less than delta. Yeah. But I need to check whether this is strictly or not strict. There's an increment coming in, so I need to check. Okay. So far, okay. 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 So why we spend a long time doing this here? This will help us prove the uniform continuity theorem. Okay, so let's define. Should we define? Should we? Yes, let's define. So we define a more general uniform continuity here. So let's say a function f. Okay, going from different metric space to another metric space. Okay, is said to be uniformly continuous if, okay, for every epsilon greater than 0, there exists a delta greater than 0, such that for all x minus 2, okay, any 2 points in our domain, if you use the domain metric on this 2 point which less than delta, it implies that the distance in the codomain matrix of the image of these 2 points will be less than epsilon. Okay, so this is the generalization of the uniform continuity you see in the real numbers, because in that case the two metric is the same. Okay, but in this case the two metric could be different. Okay, you could be different in your space as well. So what's the uniform continuity theorems then? Anyone guess? What's the general statement for uniform continuity theorem? Ah, 正刊不算。Then what imply uniform continuity? Still remember. In MA, what's the MA statement? I don't know. Do you continue? I'm not sure what's the thing behind.
On the right stuff. Epsilon.
What imply uniform continuity? Continuous at every point, okay. Then F is uniform continuous. Not quite. Your domain is quite restricted, huh? Closed and bounded. Okay, which is a closed interval. So in our setting, it will become a compact set. Okay, so if F is continuous on compact, let's say compact X, then F is uniformly continuous. Okay, no? Okay, so we generalize the idea of a closed interval in real number. It's the compact property, okay, that help you to get uniform continuity. Okay, anyone remember the proof or not in MA? How do you prove it? Huh? How do you prove it? Anyone remember? If you remember, the proof is long, that's enough. Okay. The point here is we're gonna make our life easier with the Lebesgue number lemma. Huh? So we just so we already spent a hard time proving Lebesgue number lemma, right? So now we're gonna enjoy the fruit here. Sorry? What do you mean same thing? But yeah, sure, definitely. But what's the difference here? Do you recognize there's a difference here? We pin. This is the nice thing about maths. Okay, this is the nice thing about pure maths. Is the proof is very hard, right? Very long, very hard. But we pinpoint the key point out. We take the key point out. We single out the key point. Make sense? Lemma is like we single out the key point inside the proof. This lemma could be true without knowing this theorem, you know. But history is we want to know this theorem, only then we can find the key point. You understand what I'm trying to say? Okay. Yeah. Okay. 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 So let's see how do we prove this. Well, so we have to prove from definition. Okay, for every epsilon of this, there is a delta such that this conditional statement hold. Okay, so let's do this. So in that case, let's give ourselves epsilon. All right. So looking at this epsilon here, how do we find this delta? How do we find this delta here? Well, yep. Exactly. Exactly. This is not an accident why we call this a Lebesgue measure delta here. Exactly. We're gonna use this delta. Okay. So to activate this delta, right? What do you need? You need an open covering here. Okay, you need an open covering here. Okay, so you need to build yourself an open covering. Let's say if this delta need to work in X, your domain space, so you need to somehow start with an open covering. So what kind of open covering you want to pick here? Okay, so here is the trick. So consider an open covering of X, okay, by this ball of epsilon over 2, okay, at every point Y. Does it make sense? So your Y, look at every point, build an epsilon over 2 ball. Surely cover, right? Definitely cover, because you every point you got a ball. Does it make sense? So you got a Y, right? Okay, and then at every small Y you got a ball. Small Y you got a ball. Small Y you got a ball. Okay, but you see, analysis is very tricky. When you see epsilon over 2 here, what are you expecting? What are you expecting here? You might want to use triangle inequality, something like epsilon plus over 2 plus epsilon over 2 is equals to epsilon. Then you have the thing less than epsilon. Okay? So this is what you should imagine what is coming up. Then we will use this covering here to build an open cover for our X. You know how? From this open covering here, from this open set here, you can find an open set for X. How? You know how? Remember, we got a continuous function. What's the definition of continuous function? Inverse is open. Okay, so we can consider the inverse image of these both. I think it should be obvious they cover X, right? Because your this covering contain all the images. Okay, then now like what Eric said, we can choose a delta. Okay, delta to be a Lebesgue number for this script A here, because this script A is a covering of X, which is compact. Okay, of X, which is compact. Yeah, makes sense. But remember, the weird property of Lebesgue number lemma is what? The weird property of Lebesgue number. Any B with diameter less than delta, what happened? There will be some pre-image containing this. Pre-image. So if you apply image f living inside the ball of epsilon over 2. Okay. Make sense? Okay. So then if you consider the condition x1, x2 living in X such that dx of x1, x2 less than delta, surely, okay, the 2-point set here containing x1, x2 has diameter literally less than delta. Okay, so meaning what? So that if we apply f to it, okay, because it lives in some ball, right? Ball of pre-image of ball of epsilon over 2 around y. So this pre-image here will lies in some ball of epsilon over 2. at y for some y. Okay. Does it make sense? Make sense or not? And because your open covering is using the inverse image of this kind of ball. Okay, this kind of ball. Inverse image of this kind of ball. So then the image of that set should be living inside some ball of epsilon over 2. At some y, don't know what y. It doesn't matter. Okay, doesn't matter. Why doesn't matter here? Then what can you compute here? What is the distance between fx1 and fx2 here? You can relate them to the y. Okay, so this is less than or equal to fx1 to y, and then y to fx2. Okay, but both of them are at large epsilon over 2 from y. Okay, so meaning what? Meaning it is strictly less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay, done. Okay. What did I say? What did I say? What's wrong? dy f dy. Sorry, dy no f anymore. Dy this one. Yeah, this one. Yeah. Okay. Okay. Any question? Clear? Okay. Clear? Any question? Is there an open set definition for open? I guess you can. You can, right? Should be able, right? I never thought about that. Can we do that? Can we do that or not? Anything? Can we do that? Not sure. Feel like if I didn't see it, maybe can. Why cannot? Hmm? Yeah, I mean like imagine. Okay, let's say okay. So what I was thinking is because this kind of inequality, right? You should think it as an open set, right? But within two open set, how do you discern two points? You discern 2 points inside the open set. Because what happened here is this 2 point here, right? Any 2 point in within this open set should have a different distance. Or could be different, that could be different. I think when we do the back number, then we need to know. Actually, not sure. Not sure. Yeah, I could think about it. See if it works for general topology. Okay. Let's break until 408. Hello. Hey, Junhong, can you come here for a while?
Yes. Well, we said about the topology and differential equation. So I think mostly we'll be going on the next point zero to show that that's a solution.
Okay, what's the what topology? Not sure. Okay. I'm not sure you are using topologically concept of topology like nothing. Yeah, I think better you let me know so because now the time is short, right? So if you want to change that, so you must confirm the something with me and then you
Yeah.
So why are you asking? Yeah, but even if you overstep, you why to search the PI? Okay.
我係 Michael，我們是用我給阿 Jack print 的時候，我忘 send over 是給他 print 到你要剛好也說要抽，這兩個你都是要簽的
两个都是我选，
啊，兩個都是
要抽哪一个？
我不懂有沒有抽，因為我就
你也想要抽？
因為我覺得是你的要抽吧，我確定，
那就抽了。
因為這個是只有他們兩個抽，也我代表我，因為兩個都是你簽的話，應該有必要，現在
有。
去 Liberation 待會兒，
多少年？太久。可以做啊。
因為我們用你的名義來申請，因為我們學生申請，不要只有老師能申請。
OK。
Liberation。
啊？
比你那照片都搞笑了。
这看你的好像我们在这里有什么会去老哎，我聊天。OK OK OK 好，哎，第二太忙。因为上次你们在那边做的，还有midterm，好的，然后明天是有 midterm。OK 啊，没有时间做。
我应该不写，我应该是那一题啊，还没有写完吧？
可以。对，你写那个 message 还是 email？我有一个记录。哎，不懂我要讲它有一边。什么一边呢？啊？什么一边？什么一边？啊？没有一边吗？没有哎。Rachel 讲它有一边啊，你不懂吗？我要讲有。
因为很好看，很像内脏嘛。人家涂很像内脏。
你是全部忙完了，然后忽然间松掉啊？不舒服？怎么呢？哎，我觉得是昨天那个妈妈有问题。啊？
然后我有去。
我是跟不同人去，但是他也在嘛。我觉得那边有问题。我有一点点，可是我喝了万灵药。
难怪今天听起来比较多精神。
我早上也有出去做东西啊，但是就有一点不舒服。
上一堂课已经吃了，因为吃不到
有发烧吗？
然后明天还要考试，如果这样的状况找不到，而且我现在也读不进
赶紧吃药。
吃药，
因为
去买便当。
做不可以哦，你不可以吃。连你不能吃帕拉多，你怎么办？过敏帕拉多。Aspirin 是 for 发烧的咩？
experience 我睡眠的，
哦，
不是 for 痛的咩？不是 for
它是比较
止痛的。
比
I see
我以为 aspirin 只是止痛吧？
因为我是听说失眠是
有些人来止痛，
哦，
女生对的，
难怪像熟悉，
对啦，
个名字，
对啊，是
可能，
来月经不可以吃 aspirin， 来月经就吃ibuprofen，
ibuprofen。哦，ibuprofen 不是神经发炎咩？哦，你自己是 ibuprofen 呀，ibuprofen， 对对对 ，ibuprofen。
The situation is too complex。
可以吃那个特别一点的，
我可以看看那个
啊
图啊，上一页，
很贵的，
上一页，这个
这个上一页，
上一页这个。
Sorry, I mean proof 的第一页，
这个
yes。
所以我们不要看最小的
嗯，
最小的
the band number。
最小的
啊，你可以这样想，因为有 achieve 到，对，有 achieve 到，你可以这样讲。
最小的 average，
对，有 achieve 到，你可以这样想。
then
你说这个是 kick me 啊？
最小的 average，你要最小的，中打 average，
你说 n 哪一种嘛？就不要最小就好了。
这样做了最小的 average，过去
看看哪里有用到 n。
你的 function 这里面放了 x，然后你除以我们不要直接小的，
你说不要 e/n 啊？要下课了，还有1个钟，
还有1个钟，
还有50分钟。technically。
要这样哦，
慢点，
如
不然这边会有问题。
果是 average 的话 ，maybe 有5个 en， 它选它的 value 不会有，会啊，会啊，小括。
它这个题是，它这个题的每个都没有在这里。
先上线。hello。OK。 Okay. Before we leave this compacting, there's one application here. So which we're gonna use this definition also later. So if X is a space and a point X in X is an isolated point. Okay, we're not gonna use distance to talk about isolated point here. So we say that it is an isolated point if the one point set X is open in X. Okay. If the one point set X is open, then it's an isolated. So what we're gonna do is this theorem here. If we combine these concepts together, if X is a non-empty compact Hausdorff, if it's a compact Hausdorff non-empty set, moreover, okay, this set has no isolated point, then X has to be uncountable. Can you think of a set look like this or not? Can you think of a set look like this? Can you think of a set looking like this? Compact Hausdorff, no isolated point. Compact meh? Slightly smaller than R. A closed interval Q. Q I think also not comparable. Q not comparable. Look, because the irrational not there. Yeah. Close interval 0 to 1. Okay. Okay. No isolated point. Okay, so X has to be uncountable. But last time how we show that? How do we show that the set is uncountable? We use the Cantor argument, Cantor diagonalization argument. Okay, but okay, never mind. But in this case, now we're gonna use topology to show it. Alright, we're gonna use topology to show it. Okay, compact Hausdorff, no isolated point. This X must be uncountable. Okay, if it is non-empty. So there are two steps here. Okay, see if we want to go into detail. Okay, the big two step here is first step. Okay, we will show that even any non-empty open set U of X and any point X that exists non-empty open, so open non-empty, okay, such that, so this is V, so measure this one U, this one V, such that U will contain V such that, and then okay, don't such that anymore, and X is not living inside the closure. Okay, so let's draw this picture here. So we got X, right? We got an X. Okay, and then we got an open U. Okay. And then any point X, or any point, not necessarily inside U, maybe outside. Let's put X. Here, X. Let's draw a point X here. Such that what? Such that there's another open ball inside U. Okay. But what? but X is not living on the closure of V. So closure of V means what? It can't even stay on the boundary of V. Can't even stay on it. 你给我滚远一点。对 ，OK。Okay, I think X outside U is quite, how to say, quite trivial, right? So make our life harder a bit. So maybe, how about if this X stay inside, then this means what? I could find another open set inside U such that this X is no way close to this V. Okay, no way close to this V. Not even, you cannot stay on the boundary also. 要动到我。What? Okay, sorry, this set is empty set. 0 is empty. Okay, if you can do this, okay, if you can do this, second step, what we're gonna do is, should we discuss why we can do this, or I tell you what's the next step? Are you interested or you believe? You interested? Lydia don't believe. You believe, but Lydia don't believe. Okay, let's try. So how to think about this problem here? So if can, we try not to write it down. So let's see if we can do it. So if you have an X, right, and then you have a set U, okay, how to build this V? You need to use the fact that our space is Hausdorff also, right? Okay, Hausdorff is way help you to build disjoint open neighborhood. I help you to build disjoint open neighborhood here. So, right. So let's take another point from your space. Okay, then let's in that case we throw our set 2 to the back. Let's see why we can do this first. Okay, so let's say your set got another point, right? Let's choose the y not equals to x. Okay, you must able to do this. Why can you able to do this? Why can you able to do this? If you cannot do this, means what? Maybe this open set only contain x, then x is an isolated point. But our case, we don't have isolated point. So either x outside, x inside, we still can find another y inside U that's not equal to x. Okay. Sorry. Yeah, that's what I say. Yeah, that's what I said. 你走一下绳哦 ，OK 好，你要伸回来吗 ？Spiritual 可以，我把你的绳抓回来。OK。Okay. Okay. So there are two cases, right? Could be this x could be outside the U or inside the U, but no matter what, you can find this extra y here. Otherwise, your x is an isolated point. Okay. So no matter outside, inside, you can find this. Okay. Then these are two different points in Hausdorff space, right? So what does Hausdorff space produce for you? There exists two open neighborhood such that they are disjoint. Okay, so without law of generality, so let's draw the open set like this. Okay, make sense? Make sense or not? Okay, this is what Hausdorff can give you. Should we name it? Let's name it. Easier to mention them. So let's name this W1 for X, W2 for Y. And then the green one is U, don't forget. Then the left set is X. Okay, so now how to build V then? What's the V you want to look for? What does the V have to do? V is an open set inside U such that the closure doesn't contain X. Okay, so from this picture, can you create another open set inside U or not? I want to try. 9,000. Yeah. How many open set you have here? Quite a few. Y, U, W2, W1, X. So can you create another open set inside U or not using this? That far away from X. That avoid X. W2? But W2 might not lie entirely inside U, right? Good. Okay, so good. So how about we try and set our V to be the intersection of W2 intercept of U. Surely open, right? Finite intersection. Okay. And we claim that this is the desired open set. Okay, to say that this is a desired open set, what do we need to show? What do we need to show? We need to show that finally we need to show that X is not in the closure of this intersection. Okay, it doesn't stay inside the closure of this intersection. Okay, otherwise what could happen? Otherwise, what could happen here? If we stay inside V bar, what could happen? What could happen if we stay inside V bar? Hey, do we have any theorem on this bar thingy? About compactness, about disjoint. Do you have this kind of statement or not? Do you have any statement like okay, so otherwise what happened? So first we know that Y will stay inside V, right? Okay, because Y is a point in W2 and in U. Okay. More importantly, V here is a subset of U. Okay, this is subset of U. And then next, we want to claim that not otherwise. This is first checking. Oh, this is the first check. So we want to check that actually V is a subset of U. And then second check. So our second check here is we want to show that X is not in V bar. Any contradiction if S stay in V bar here? S stay in V bar has what property? Either X is in V, but for sure X is not in V. What's the other probability? What's the other property? X is a limit point. Limit point of Y. X is a limit point of, so if you are staying in a V bar, meaning you are the limit point of V. And limit point of V means what? Limit point of the set. So if you build any neighborhood, you must intersect V. But we got a neighborhood that doesn't intersect B. So that okay. Limit point is every neighborhood of X. So if X is a limit point of V, meaning any neighborhood around X must intersect B. But there's a neighborhood that doesn't intersect B. This is how we pick the W1, W2. Okay. Yeah. Right. So how on earth we're gonna use this kind of statement? So step 2. Okay, step 2 is we show that any given function from the positive integer to x, okay, this function cannot be surjective. Cannot be surjective. Huh? Oh, and also can. This, you mean this one n? Yeah, also can. Okay. It's not surjective, then it follows that x is uncountable. But the Cantor diagonalization argument is just one of the map. Okay, that map doesn't work. But this map, this will produce, if you tell me that, oh, I got a map from Z class to X, this kind of map is never surjective. Okay, more general. Let me show a general map from positive integer to X. Do you want to see this? Lydia still want to see it? Okay, good. So how do we show not surjective here? So we want to show that there's some point in X is not met by some positive integer. Okay. Okay. So in that case, let's take the given function here. Well, this function, what's this function doing? This function is just picking out a sequence. Okay. Picking out a sequence. F1, 1 point, F2, 1 point, F3, 1 point. Okay, it's a sequence. In a Cantor diagonalization, the sequence is like binary number, binary expansion, right? Okay, but this one general. Okay, don't care. So meaning from this sequence, you want to find some point that you can map to. So how to do this? How can we use step 1 to do this? Okay, how do we use step 1 to do this? What's step 1 again? Let's remind ourselves. So any open set, okay, any point, okay, you can find another smaller v. Okay, a smaller v. Okay, such that this x cannot stay inside the closure of this v. Can't even touch it. Okay. You mean you understand what I say? You understand what I say? Can you imagine an inductive statement from here? If I got a u, right? Okay, I got a point inside here. I can find a smaller open set such that the closure doesn't include this x. Then what's the next step? This v is a new open set. Play the same game. Play the same game. From inside this v, have a smaller v prime such that huh? Good. Yeah, so you can find another point inside v such that you can avoid that point. A smaller open set that avoid that point. And then you go into it. Then you go into it. Okay. So let's do it. So what we do is let's apply step 1 to the non-empty open set. Open set u, okay, which is equal to x. To choose a smaller one, okay, let's say smaller one which is non-empty open set. Call it a v1, okay, in x, such that this v1 bar will avoid x1. Okay, this x1 picking from the image of my function. Sorry? See? Avoid S1. Oh, thank you. Avoid S1. Okay. So, in general, we're gonna pick a chain of Vn. Okay, so given Vn minus 1 is open and non-empty, okay, we can choose Vn to be open, non-empty, such that Vn contained in Vn minus 1 and Vn bar doesn't contain Xn. Okay, so in this case, we got a nested sequence here. Okay, consider this nested sequence. V1 bar, V2 bar, blah, 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 blah. Okay, make sense? Make sense, huh? Okay, good. So this is a sequence of non-empty closed set. But our space is compact. Still remember, compact apply to closed set. What's the statement? Huh? Finite intersection property, right? Okay, so by compactness, if you take the intersection of all this, it should be non-empty. Okay, by compactness, there exists a X in the intersection of all closed set here. There should be something inside there. But this point here shouldn't come from your Sn for all n. Shouldn't come from it. Why? Because this is exactly how you build your Vn. Okay, your Vn bar will avoid all the Sn. But there's still something inside this intersection. Yes? Hi, 什么意思？这 V 什么？我们没有用 X 吧？有没有？我们有用 X 吗？没有啊，在这个 proof 有没有？没有。哦，I mean，you mean 这个 X，这是 any X。But step 2里面我们没有 S。Step 2我们是用 Sn。Sn。So, this Vn bar here will avoid all the Sn. This Vn bar will avoid all the Xn, right? Sn, okay? But there's still something else inside the intersection. Okay, and this X cannot be any Sn, okay? Because this Vn is chosen to avoid all the Sn. Okay, make sense? So this is something not in your image. Okay. Yeah, maybe you can use you can try to think about Cantor diagonalization using this kind of argument. Okay, what? How to think about that diagonal point? Not sure if it's helpful or not. Can try. Okay, so corollary is every closed interval in R is countable. Okay, so this is a topological proof. Okay, make sense? Any question? Or question? Any question? Okay, I'll just
What happens?
What do you mean? What happens if it is countable? No. I mean this uncountable is necessary condition. You cannot change. You mean what kind of property can make your X countable? Well, yeah, that one is a big detour actually. It might not be might not be related to this. Usually what we will do is we will change sufficient condition and then see what happens. See whether the results still hold. But if you want to think about countable, then there's a different story, I guess. Okay. So how do you imagine this theorem here? So if you got a Hausdorff space, right? So every 2 points, you can separate them. But no isolated points means what? When you separate them, you cannot use singleton to separate them. There must be something else inside the open set. Okay. There must be something else inside the open set. Yeah. To form your open set. To form your open neighborhood. Okay. And then what's another property? It's compact. Okay, it's compact, meaning what? If you look at these are the open cover, right? You should have finitely many of them to cover the whole space. So how do you imagine this animation? Maybe if you can make animation, maybe you can try and make this up. So what do you imagine in your mind? You have singleton. Okay, can't be open, so must have some other point inside this open set. But only finite cover. Okay, finite cover that can how to say? Finite cover. Yeah, finite covering to cover the whole space. So all these points have to squeeze together. Squeeze into finitely many covering. Squeeze. 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 Hey, how about think about why cannot be 2 point set? 1 point set cannot, right? Because it's isolated. How about 2 point set? Why 2 point set cannot happen? You want to think about it or not? Then you can imagine the picture already. Why 2 point set cannot work? Yeah. No isolated point meaning there's no open set content 1 point. Yeah, meaning this is a discrete topology. Yes, very good. You listen what he said. If you don't have singleton here, how is it Hausdorff? You only have discrete topology. You cannot separate these 2 points. If you're gonna separate these 2 points, means what? There's an open set content this point, content this point. But this become what? Singleton, which is isolated point. Okay. Then on the other hand, you need to be Hausdorff. So cannot no. Cannot be 2 points no. Okay. Add one more point. Since 2 points doesn't work. This is how you work with max. You need to try. So if you add another point, could it be? There are 9 kind of topology we had, right? On this set. But you don't want the topology that includes singleton. Otherwise, you got isolated point. So what could it be? Like this, like this, like this. Also cannot, right? Because this is a topology. If you have this kind of thing, singleton must appear. Doesn't work again, no? Squeeze, 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 squeeze. Okay. OK， 哇，这个像什么？你知道吗？电风扇，差不多像电风扇，这是沙林感。Ouch， 没有看就更紧。下面接轮演这个。OK， Anyway，OK。 Okay. Right. So let's go to next part. Next part, I will use slide. In this part here, I want to bring out to you an idea of one point compactification. Okay, locally, compactness is not very, very interesting by its right. I mean, at least for this class, we won't focus such detail. It's like how we treat locally connected. But I want to use this concept to bring out this one point compactification here. Okay, this is one of the accent of this class. And you use one point to compactify your set. Your set might not be compact, but I put one point into it, it can compact. Okay? Maybe some of you will be reminded on your AG class. Okay? One point compactification here. So the slogan here is any locally compact Hausdorff space can be embedded in so don't need to worry about whether it's E or I here. They are the anonym in this class. So you have the injective map embedded in a certain compact Hausdorff space. Okay, and then this compact Hausdorff space is called the one-point compactification of that locally compact Hausdorff space. Okay. Okay. Make sense of this question? We don't know what is locally compact here, but if you have a locally compact Hausdorff space, we can put it inside a compact Hausdorff space, which we call it a one-point compactification. Okay, it's not clear why only one point is enough, but later we will see some theorem. Okay, but this is a slogan for local compactness. So what's local compact then? So a space is locally compact at a point, okay, if there exists a compact subspace, okay, of X that contain an open neighborhood of X. Okay, so meaning what? If you have a point X, okay, then you can find a compact subspace, okay, that contain one of the open neighborhood. Imagine. So whenever we have this definition, right, space, make sure you draw space inside. So you got a space X, and then you got a point X. Okay, if you have some open neighborhood here, then it will be contained inside one of the X subspace. Okay, if you can do it for every point of X, then your space is called locally compact. Okay, so remark here is a compact space is automatically locally compact. Okay, so for example, R is locally compact. Okay, R is locally compact here. It's not compact, but it's locally compact. It's not compact, but locally compact. Why? Because you know that the closed interval is compact. Okay, so meaning if you have any X here, and then you look for living inside some compact set, then there's an open table. Okay, so 每次你们不是讲，哎呦，好像 RU compact, U full compact, so we make it precise here. What do we mean by that? Okay, it has a compact subspace, and then this compact subspace can contain an open neighborhood of X. Okay, it has a compact subspace, but it's not compact. Okay. So R is locally compact, and then you can show that Q is not locally compact. Actually, this proof is quite interesting. Should we share it or you read it yourself? Can you read it yourself? Okay, this proof actually quite interesting. There's a nice picture on this. Very, very pretty picture here. Okay, it's not locally compact. Although there's a lot of notation here, but it's a very, very geometric. Which one? How do you read this diagram? So I got a labeling for here. Labeling for you here. Okay. So this complement set I labeled by this red dot, and then the thing inside this union, right, is the orange. Okay, so it's a union of these bit, and then the yellow bit here is the other union part here. Okay, so it's this bit here. Okay, so you combine all these together, so you take the union. And then somehow you see that this is a infinite open cover without a finite subcover. Okay, but I don't want to go into this technicality. Okay, the theorem here is when is X is locally compact post off here. So now you should imagine the R examples because I show you that R is locally compact, and then we know that R is post off. Okay, so let's imagine this theorem with R. So R is already locally compact post off, so meaning the below must happen for R. Okay, so what should happen for R? There exists a space Y. Okay, there's a space Y such that X is a subspace of Y. Okay, here it means subspace topology. Right? And then Y take away X is just one point. Okay, and then Y is a compact Hausdorff space. Okay. And if you have another Y prime that does this, actually there's a homeomorphism between Y and Y. Alright, so meaning actually this thing will form a equivalent class. Okay, that's why we call it a one-point compactification. The one-point compactification under this equivalent class. Okay, can you imagine what thing does? I mean, what's the Y that R need? What's the thing that that you can get for your, if let's say what happened if X is R? What is Y? Can you imagine? Y is just X plus a point. What is it? What is it? Y agent lap. What is it? Apa itu? No lah. Not RP1. Not RP1. What is it? Could be isomorph. I mean, could be homeomorphic to RP1, but complex number so far away. You just need 1 point. Yeah, from infinity. So what do you get? A circle. Okay, so a line plus an infinity point. Okay, you got a circle. Okay. Now, obviously, you need to show it. Obviously, you need to show it. It's not trivial here, but what do you need to show it? You just need to show 3 things, right? How X is a subspace of Y, and then maybe this one requires some work. Y take away X is singleton, I think, obvious. And then you need to show that Y this X1, the circle here is Hausdorff. I think it's not too much. You can use parametrization. But this proof, not going to prove to you. You can find it in Moncrief's theorem 29.1. But what I want to point out here is whenever you have locally compact Hausdorff space, you can find its 1-point compactification. Okay, so from here, what we can generalize is if your Y is a compact Hausdorff space and then X is a proper subspace of Y1, Y, whose closure equals to Y, then Y is called the compactification of X. Okay, so you start with any proper subspace of a compact Hausdorff space, then Y is a compact Hausdorff space for the proper subspace. But if the complement of X is just 1 point, we call it a 1-point compactification. Okay, meaning you put 1 point in, it becomes compact. Make sense? Okay. Yeah. Okay, I want to introduce this as a language, if not the technical part. So what we see here is if your X is real number, you add 1 point in, what you get is actually S1. Okay, you should convince yourself why X1 is compact Hausdorff. I think this is not hard to see. Okay. It's compared also. What is S1? S1 is the okay. In this case, I didn't draw any parameterization here. Okay, but because different parameterization or even different size, different radius, different center, we will have a homeomorphism between them. Okay, so it doesn't matter for now. But if you really want to show that it's comparable, then maybe you need to fix one parameterization. The one that you want to look at usually is the easiest one, the one you see in calculus 2, the unique circle. Yeah. If you change the radius, change the center, these are homeomorphism. So the topology won't change. So that's why there's no more coordinate here anymore. Okay, they are all homeomorphic already. Make sense? Okay, the property won't change. You 不可能大的 compare 小的不 compare 的，可能大的 hostile 小的不 hostile 的。Okay, so this property doesn't change with size anymore. So that's why you will see in the maybe some of the videos on topology. All topology can change size one. Why? Because they are homeomorphic. Our property are true up to homeomorphic. Okay. And then how about R2 then? If R2 I put a point in, what do I get? Okay, what I get is a sphere. Okay, actually. Okay, if I add 1 point into it. How to show this? Why is it a 1 point compactification? You need to show the 3 things. Okay, you need to show the 3 things. Okay. And then let's say it's not R2 anymore, but this R2 got complex structure. Okay, so complex structure means what? The y direction got an I there, meaning what? If you want to multiply two y together, it will become minus a real number. Previously, if you multiply two real number, you get real number. But here, if you multiply two y coordinates together, you get a negative of y. Become real. Okay, so this is what we call a complex structure. So complex analysis is about learning these complex structure. What happens if you put complex structure there? And then with complex structure, another name is called conformal structure. Why conformal? Actually, this structure will preserve angle. Okay, so what you learn in complex analysis is something that preserves angle. Okay, so your R2 with the conformal structure here, you put a point in, still S2, but this S2 is a special S2, what we call a Riemann sphere. Right? This is what we call a Riemann sphere. However, when S2 comes with a complex structure, then we call it a Riemann sphere. Hopefully, you see this in your complex analysis. Huh? You see it? Okay. Okay, good. Okay. Any questions so far? Any questions so far? Okay, before we go, maybe I disclose something to you first. We will go back, regress a bit onto sequential compactness. And then we will see the relation between open cover compactness and sequential compactness. And how they imply each other, and then which one is stronger, where in what conditions they're the same. So okay. There are two things, there are two. Sequential is what you learn in MA, right? There's another compactness is linear. Okay, so there are 3 types of compactness. Let's see how they relate to each other. Open cover compactness, linear point compactness, and sequential. Okay, see you next week. If you need the extension for your assignment because your midterm, right, please write to me. Don't write after the deadline. This is not a good word culture. You should do it before the deadline. Please do it before deadline if you need, because some of you request, so you can request. What?